I'm Marko Topolnik from Hazelcast. I'm one of the original engineers who built our Hazelcast.Jet distributed stream processing engine, and I will present to you a few features of the execution engine, which I spent most time on. So let's start with a general introduction. Here's an example of the code you write to use Jet. You can see it's Java code, and it uses lambdas and higher order functions. So it looks like a lot like Java util streams, if you're familiar with that. We just take the lambdas you write and we serialize them, and that's how distributed computation can work for us. On this slide, on this example, you can see that we can use both infinite streams like Kafka topic, as well as finite data sets. In this example, we have some table of buyers, person entities. And then in this example, you can see that we perform some computation, aggregation of the finite data set, and then we use hash join operation to enrich every event, every order event with the computed data from the finite data set. So in the previous slide, we saw some of the features like hash join. Another very important feature that we have is windowed aggregation, and specifically the sliding window. Basically, when you want to aggregate data in an infinite stream, what you have to do is pick a finite subset of that stream, and most typically the most recent part of the stream, and apply aggregation to that. And then the point is to keep this aggregated result as recent and as fresh as possible. And with the sliding window, the way we implement it, you can achieve updating the sliding window results 100 times per second with very low latency. And we'll see that in the example that's coming up. But first, let's talk about the execution engine. And for this, I will use another example, which is the kind of the most familiar one for as examples go in stream processing. It's the word count, basically calculating word frequency over a body of text. You can see there's a flat method filter state. So this is stateless processing that transforms lines of text into words, and then we group by word and perform a count. So this is how it ends up being executed. So this is like the execution plan on a two-node cluster where every node has 2 CPUs. You can immediately notice that every computation step is replicated 4 times because there are 4 CPUs involved. So every CPU performs all kinds of work on part of the data. That's how we do it. So basically, there's just a total of 4 threads doing all the work. One thing I would also point out here is that the communication between steps is done over single producer, single consumer queues. So every one of these arrows is another concurrent queue. And when you have a single producer, single consumer queue, basically you don't need any contention resolving like compare and swap operations, which are quite expensive. Another thing to note is that we maintain data locality as far as we can, so we don't send data to any other nodes unless strictly necessary for partitioned distributed computation, as we see here. So in this step, this was grouping by word. Obviously, if you want to count how many times a particular word occurred, you have to let one particular task observe all the counts for that word, so that even if the word came from another node, you still have to observe it on the node responsible for that word. So only in this case we actually send data across the network. Another feature of our engine is, I already mentioned it briefly, you can see here 4 tasks here, 4 tasks here on just 2 threads total. And how we achieve this is that a task, we call it actually a tasklet. So it's not a standalone task that would occupy a thread with its loop that processes the data. And actually it's code that can yield back to the framework as soon as it is blocked for more work. So basically the output queue is full, the input queue is empty. In all these cases, you can just suspend your execution and return control to the framework, which will then be able to proceed with computation for another node. And for sources and seeks, this is typically involving outside libraries with possibly blocking I/O. So if needed, we can also create more threads for those kind of special cases. Now let's go to the benchmarking that we did. We used the Nextmark benchmark suite, which is kind of a standard suite in this space, which deals with auctions, online auctions. This is an example of query 5, for example, which turned out to be the most heavyweight one for us. And you can see it was a sliding window, which we mentioned with the grouped aggregation. And then following that, another aggregation to get the top 10 counts from the previous step. So this is why it's the most heavyweight one. And here we can see an overview of all the latencies. So what we are looking at here is 99.99% latency, very high percentile latency in a cluster up to 20 nodes with 10,000 distinct keys involved. And what you can see is that this worst case for us was 16 millisecond latency to output window results of those cascading windows. So another thing that we did, another measurement, was to measure the highest throughput that a node could perform, basically how much you can process per second until the pipeline just keeps lagging behind and never catches up with the data. And for one node, we got 25 million events per second. And from then on, adding more nodes, you just get every time, every single node you add, you just add 25 million more events per second, completely linear scaling. And flip side, latency of the same measurement. So how we did, basically to get the maximum throughput, you have to push the throughput as high as it will go and then back off a little bit to find that exact spot where the pipeline is still hanging on and keeping up with the data. But then the latency is not the best. So to get the latency measurement for a reasonable throughput, not the maximum throughput, we reduced it to 80% of what we measured as the highest throughput. And then we measured the latency. And you can see in the worst case, now with 40 nodes, this toughest query for Jet was still 26 milliseconds of latency. So thanks for attending. This is all I have time for, and goodbye.